slides as time allows, which probably will allow a little less now, at the end to go over just some of the more features of Azure Files for those that aren't fully aware of it. This is just SMB protocol history. You can refer to the slides later. We're up to Win 10 now. Fundamental Azure File Service is not just running the Windows file server on Azure. You're not running cert2.sys. It's fundamentally different. It's a complete rewrite of it on top of what is a block store, effectively, our object store, which we use Azure Files and tables for. And it's very different than just trying to share a cert2.sys partition. Azure Files has highly available tables and blobs, and that are both redundant and durable and highly available. And we leverage that ability into making Azure Files have the same attributes, because that is actually our backing store. And we use Azure Tables there are no SQL tables as our metadata store, because it actually lends itself really nicely to the sort of attributes you store about files. Azure right now, we're currently at SMB 3 with encryption, persistent handles, and directory releases. 5 terabytes per share. Just on Monday, announced our new 100 terabyte per share private preview, which is large file shares. And I'll get into how we accomplish that later. And that's actually the major schema impacting change. 1,000 IOPS per share is now up to 100,000. It depends on whether or not you're using premium, which is SSD backed, or non-premium. We have added per file ACLs, along with Kerberos authentication and Active Directory integration. This was really a major requested feature. So companies could more seamlessly integrate their on-premise domains and Active Directories into Azure Files. Right now it's Azure Active Directory, which is a little different than normal on-prem Active Directory, but things are heading definitely towards merging in the same direction. I'm not an Active Directory expert, so I won't be able to go into a lot of detail on that. We've added share snapshots, which are completely the same as a snare snapshot on a Windows server using the virtual disk service. And it creates basically a snapshot in time on a per volume basis. So in our case, it's a per share basis. And it behaves just as if you had done this on a normal Windows server. And you can access it. In Windows, if you're on folder, you can do right-click as in previous versions. And that's how this uses that. So that just works correctly now. There was a problem with some higher Unicode characters in this private use area that had to do with the version of Windows we were using, and we've actually now upgraded and fixed that, so that limitation should be gone. There are still some NTFS features we don't support. We don't support name streams. Sorry, Jeremy. Yet. And so there's some of the more features that are less demanded we don't support yet, but definitely it's just a matter of time, really. It's just priorities and priorities, which features are most important. This is our current Linux support. Directory release support has been, I guess, checked in, the mainline kernel. We're just kind of waiting for it to percolate. Otherwise, you can see almost everyone supports encryption, and then everyone supports persistent handles. Persistent handles are very important for Azure Files because that's actually what makes it a usable platform. Because our service, our front ends, we upgrade it so often that we end up breaking connections all the time, like once every few days at least. And that has to be seamless for the application. And the persistent handles allow that to be seamless. It's part of the continuous availability of Windows clustering. And so we were able to leverage that to create, to have Azure Files have the appearance of absolutely zero downtime. This kind of shows how you would access an Azure File share from outside the cloud over the internet. You basically have using SMB3 encryption. We require encryption if you're coming in from the internet. And it comes into the, does this have a pointer? It comes into our what's called a software load balancer, which we have a single VIP, a virtual IP address, that your share maps to, but that's basically then gone and sent to several front ends, which the software load balancer hashes the TCP/IP headers to figure out which, kind of more or less randomly, which front end gets that connection. And then those all talk to our table and blob store backend. And if the network isn't working, unfortunately, so I can't do the demo. I've tried 3 laptops, sorry. What's enabled by AFS, Azure File Service, is you can basically, since it is just regular Windows APIs, either C runtime or Win32, just create file, open file. You can take existing applications, and without even recompiling them, they just work. Now, it's important to understand that there's a performance differences between running locally on your local disk to running even against a local share on-prem, so basically a server inside of your data center. And then when you go and stretch that across over to the internet, all the latencies get much higher. So the performance characteristics are different when you're talking to a local disk, a local file system, and directly connected storage, as opposed to especially over the internet to Azure Files. So that's something to take into account. Certain less than efficient behaviors of an application that might not have been noticed on-prem, talking to either a directly connected storage or a local file share, you will notice on Azure Files. And I have some slides at the end to go into that, but it should be pretty clear. We also offer a REST interface that has that's a shared namespace between REST and SMB. So if you really want to go and say in the future transition your applications to be more RESTful, rather than having to go and make a switch all at once, you can continue using your existing applications. And then with shared the same namespace, the same data, you can seamlessly transfer over to REST if you want to. And these are basically all the REST APIs that are offered. This is again that showing how requests come into Azure Files through our load balancer there, and picks a random front end and then goes down into the file system metadata, and the file data is stored in the blob store. And the idea of state here is one of the state tiering that's interesting is that you're able to go and store, like for instance, state about the connection in the front end and not have to durably commit that, because if you disconnect, it doesn't matter, it's gone. But states about, like for instance, a handle or your current session ID, that all has to be durably committed, because when you lose your connection or your front end is rebooted and you reconnect to a different front end, that all has to be rematerialized so that it's as though nothing happened. Your client is able to seamlessly reconnect. Azure Tables is a NoSQL table, and we have a set of tables within that we use, and we're able to group them together. We have one table, which is our main file table that has both rows for files and then entries in the namespace. But then there's several ancillary tables that have to do with byte range locks, for instance. Handles is a separate table for handles and leases. And Azure Table allows us to go and create single atomic transactions across a set of tables and a set of rows in a set of tables. So it makes it really easy to implement these sort of file system operations, because I can simply say I want to begin a transaction. I can make several modifications to different tables, different rows, and then either abort or commit it. And so a lot of those really hard problems are solved for us with one major caveat here, is that at the very last bullet point, that as long as they're within a partition. And a partition means that the parts of the tables, the section of rows of each table that you're looking at are all currently owned by the same physical node, back-end node, basically a single computer. And that's how it's able to maintain that atomicity among transactions. And that becomes key later on. Also, rows have two types of keys, partition keys and row keys. Partition keys specify where we block things in terms of ownership among that section of the table, among different back-end nodes of who is currently the owner of that range of the table. Row keys are not about which computer owns it. They're lower down in the hierarchy, but they allow you to basically sort or search by a range of key values. So we're able to again leverage this capability that Azure Tables provides of having the really simple ACID semantics. Again, as long as the ranges of all the tables that we're interested in are hosted by the same backend node. And we're able to go and by having these partition keys, currently in version 1, what's the currently deployed worldwide in production, that partition key boundary is a share. So what that means is for any given share, all the interesting ranges of all these tables that correspond to your share are all at any given time owned by a single backend node, and that's how we're able to do atomic transactions across any operation within that table. In private preview, what we've added is the ability to have what we call large file shares. A share can now span across multiple partitions, and what we've done effectively, and I'll have a slide showing this graphically, is that we've basically gone and moved our partition key over to now encompass the file ID, which is like the NTFS file ID or an inode ID, and it allows us to partition a volume now into smaller chunks. And we're able to then spread that load further. Important thing here is that this couldn't be just a new feature for new accounts. It had to be basically everyone would just get this ability. And this is difficult because when you have huge amounts of data, all backed by a schema, and then you try to change that schema on the fly, it's a challenging process. And you're trying to do it in a way that is absolutely seamless so that the customers have no idea what's happening underneath them. And that's the bulk of what I want to talk about here. But I wanted to give some of this background here, as it's really important to understand the underlying principles. These are some of the tables that we use within Azure Files. The main one is the file table, which has different types of rows. And one is for namespace and one is for file. And it's very similar to other file system architectures, the way they split namespace and file ID. Pages is where that corresponds to the page blobs that actually hold the physical file data, the actual data, which is held by nodes that are called extent nodes. The handles, leases, change notify, byte range locks, and there's other ones, events for change notify. Those are kind of the main big ones. So this is our row key. This is the Azure file table row. This is the most important one. And there are two types of file rows, namespace and data, and that little thing that you can't read there says that they're actually technically one type of row. What we've done is there's actually a column called a row type, and it's a partition key. And so it kind of changes what the identity of different columns in that row. Though conceptually, it's more like two different rows. And so I'm showing you here for two different rows because this actually makes it easier to understand. In the namespace rows are partitioned by account name, share name, and then the row keys. This is how we basically do DIRs and parent ID and file name. Share version, that's for share snapshots. So the idea is that anytime when you take a snapshot and you reopen a file, we're able to go and create new share versions, and that's how we create this kind of almost illusion of volume-based shares, a volume-based snapshot, because we're not actually a block storage. In Windows, VolSnap is a block driver. And so it literally is creating multiple volumes, and so there's no changes in NTFS for volume snapshots to work on NT. It's because it's a lower level of volume device driver. It just materializes these virtual volumes that correspond to that snapshot time. We don't have that. We're not a block store, so we had to basically go and create this illusion that that's what you had, and by keeping track of all these different versions of directories and files, which was an interesting way to do it. It was very different than the way VolSnap did it. Was actually maybe easier, but again, we had a name-based data store. Now the data rows, these correspond to the actual files. Think of them as like MFT records, master file table records in NTFS. And in current production here, we have account name and share name, again, partitioned by that. What that means is for any given share is wholly contained within a partition, which means it's wholly owned by a single backend node at any given time, which makes it very easy to do these transactions. This is a change that we've done. So we've moved the file ID into the partition key. And we also go and we flip around file ID so that we get, even though it's incrementing atomically, it creates this really wide dispersion. So you get a really nice balancing, even if you're just creating files sequentially. And you've probably noticed that if you queried your file IDs on Azure Files, there are these huge numbers, and it's because they're flipped around. What this means is that for a single share is going to be split among all these different partitions. And that allows us to basically go and distribute those among many different backend nodes. Again, we're doing this for existing accounts, not just accounts that are brand newly created. And so you have this problem that, well, I've got all these existing accounts, all these existing files, and all these existing open handles, and all these existing pending change notifies, and existing everything, right? I mean, it's a fluid system, and all this stuff is happening. And I want to go and change this fundamental partition, this schema under the covers. And so the way we've done that is, first of all, by having a background process which just goes and lazily goes and converts them all. So for files that are open, we have to go and make copies of some data between what's in the namespace rows and what's in the file rows. For instance, handles. Because one of the ideas here is that we don't want to have to go and talk to the namespace node. I'll get that in a little bit. If we're just doing reads and writes, we can go talk directly to a backend node. That allows the greater scaling. But what that means is we actually know how to replicate some of the handle state and lease state that used to be able to be in a single partition, now has to be replicated, which doing replication is difficult. And so we had to also, when we're doing this initial in the background, preparing it effectively for large file share, that also was something that had interesting synchronization issues, because you have to be very careful of requests coming in and just race conditions. And there's also the problem of people start using handles before we've gotten to their particular file row. And in that case, we have to go and basically do it on the fly, do this conversion on the fly to this new file share schema, as well as making sure we're not conflicting with this background one. There's all these race conditions you can imagine that can potentially happen. And so you have to make sure all this is correctly synchronized. And you have just unit tests that stress this and create artificial race conditions. But this is how we basically accomplish this seamless change kind of under the covers effectively, so that we're going and changing the partitioning of the whole file ID space without the customer being aware of it. This is how Azure Files maps to hardware. Those front-end nodes I showed that the software load balancer connects to, these are the ones that basically the user effectively has a TCP connection to. And for any given session, once you connect to a front-end node, all your requests will go to that particular front-end node. And then this is the current deployed Azure Files in production. There's a single backend node for any given share, and then everything kind of goes to that backend node, and then the actual file data is stored on the EN nodes, which stands for extent nodes. And this is what's happened now with large file share, is that the backend nodes where there used to be one, it's not backend node 0, that should be backend node n, EN node 0, node n. But the idea is we're able to scale among many different nodes. The actual EN part hasn't changed. That's still the same in terms of how the actual file data is stored. This is a topology showing how the front-end nodes talk to back-end nodes. Before, again, we had a single back-end node, and that would, for metadata and file write data, all the writes would be sent through the back-end node. We had an optimization for reads, that reads were allowed to go directly from the front end to whichever extent node was backing that particular bit of data that you needed, so that any front-end node could talk to any EN node without going through the back end. There was some mapping information it had to get, but once it had that, all the data was, for writes, there's complications around extending writes that made that more difficult, but reads were able to do that easily. In the new schema, what we have is we still have a single back-end namespace node. So that node owns the whole namespace, which means we can still take advantage of the Azure tables atomic ability to make transactions across multiple rows and multiple tables very simply. And by having all the namespace operations owned at any given time by a single backend node, that allows us to the most difficult operations, things like rename and close. Close is amazingly difficult because in Windows, the semantics are that when you close a handle, that's when you kind of do all the stuff. And so close actually becomes a very heavyweight operation. It can be, depending on what you did with the handle or what other people did with their handles. And so this is where kind of the more scaling happens. For write data now and file metadata, we're at file metadata being like file size and byte range locks. We're able to go and talk directly to the backend node that's hosting that particular sliver of the file ID space. So remember again, we've partitioned the file ID space. So you have an open handle and that has a specific open file ID. And so when we come into front end node, we know exactly which backend node is serving that range of the file ID space. And we're able to talk directly to that backend node. And then again, each one of those can then fan out to all the different extent nodes. And again, read is able to go and it's a many to many, just as it was before. With this one caveat that we do have, that's why that metadata is in orange, and I have a little thing, it doesn't go all the way to EN because you can only do so many colors in these sort of things, or else it gets really difficult to read. But the idea is we do have to, even our reads, we have to get some extent information from the backend node, which just tells us where the data lives. This is reinforcing the idea of multiple table requests, how we're able to go and since a namespace node is owned by is within a single partition for a single share, we're able to go and make operations. We're able to make transactional operations across multiple tables. And so for things like rename or create and close, where we have to update multiple of these rows, like creating a handle at the same time that we're incrementing an open count, we're able to simply go and call an API which just says start a transaction, make all these changes, and either commit or abort it at the end. And that used to be the case as well for all rows, but now with these partitioning the file ID space, we now have to do distributed transactions. For instance, creating a handle row for the backend node that's holding that sliver of the file ID space that you created the file. Because again, the front end node has to have some way to verify it. And so we have to do multi-step with different types of distributed transactions depending on the nature of the operation. And we leverage as well the ability that since we're always up, we can effectively have in perpetuity roll forward. We can make assumptions that we'll eventually get to rolling something forward, and so it makes it easy in that sense. All we have to do is start committing begin records, and we know that even if something stumbles on it, we can just get that done first and then go ahead and do what was behind it. So we have this assumption we can make that will always exist. This is important in that picture that I showed that had the many-to-many, is that we have active-active high availability clustering. And this is with giving out read leases and handle leases. In the Windows clustering, they actually restrict the read leases, I think, maybe handle leases too, for their persistent handles. But we actually give all those leases, which means that all those clients can all individually cache all their data as well. It looks just like multiple people reading and writing this. Well, when multiple people start opening the file, then you can't write anymore. All the writes have to go. But you could have multiple readers to the file, and that's all completely works because they also have the read leases. And they have their handle leases as well, so when the client application closes its handle, we don't have to send the close right away. And this reduces the chatter substantially. By the way, I was talking to some Linux people yesterday and just casually mentioned in my slide that we've added directory leases. That was just kind of a casual mention, but evidently directory leases are very important in the real world, because what that lets you do is basically keep your directories. So you do a dir, and you don't have to basically go and have some fake timeout that you go and do a refresh on, and that's not even correct anyway. No, you basically have this directory lease, which means you get notified if anything in the directory changes. And so if you have applications that do a lot of find first, find next, this reduces the network chatter substantially. And yeah, again, just adding that distributed transactions have complicated this picture substantially. We've actually been working on this a long time. That's why we've been working on this a long time, is because it's very hard. This goes into some of how we tier state, and this is kind of going now into more of the background of Azure Files and some of the content that I've dealt with in previous talks about Azure Files and the overall design architecture of it. We have this idea that we want to go and separate state by what has to be durably committed and what doesn't. And we're able to go and put state that doesn't have to be durably committed and keep that in the front end. For instance, in SMB, if some of you guys are familiar with SMB, there's a file ID has two different components. It's actually really a handle ID, but it has a volatile and a persistent state. The persistent is what maintains if you reconnect a handle. There's this volatile part, and that's only valid for the current session. And since, by definition, when we have a connection break, we establish a new session, we don't need to durably commit that volatile ID. And so we can keep that just in the memory of the front-end nodes, and by not having to worry about committing things that don't have to be maintained, that simplifies our architecture as well and is more performant. And there's a difference between state which has to be durably committed but is not changeable by the user, versus state that is changeable by the user. Things like handle ID, the numeric handle ID, versus like file size, for instance. Both those have to be durably committed, but one is changeable by the user and one isn't. This is going more into details about some of these, the difference in state between different pieces of metadata, such as file ID. Whether something is a directory or not is immutable. There's no way once something is created, it's either a file or directory, it can't change. And so the front end doesn't have to ask that question again, say, is this a directory, is this a file? With persistent handles, some of the state is maintained by the client, which is extremely helpful. There's a create GUID that is passed in whenever you open a persistent handle. And when it reconnects, it passes us the same create GUID. And that allows us to detect replays easily. Because by having different physical nodes for our front-end nodes and our back-end nodes, there's always this possibility that the back-end node did successfully open the file, but the message never got back to the client before a disconnect happened, which means the client's going to try and reopen that same file handle again. This allows us to basically say, oh, that actually already worked. I couldn't tell you about it, but I actually did already open it. And then it becomes effectively a no-op. And then we send the reply back. And so, again, to the client application, this is perfectly seamless because it simply gets reopened. Some state, potentially, is open counts. We have a thing called geo-replication in Azure, which is an extra feature. And what we have is the same data a file data is replicated in a different data center at least like 500 miles away or something. So basically, it's not susceptible to the same sort of physical disaster, like a hurricane or an earthquake. Actually, earthquake maybe, but some of this state, which would be very expensive to synchronously replicate, like open counts, we don't do. So all the file data is replicated, and there's even a delay in that. But that's a trade-off between something which should really almost never happen. But if it did happen, you don't want a whole disaster of losing all of your data. But if a data center was taken out by an earthquake or a tsunami or something, the fact that you have to reopen your handles is not that big of a deal. This shows how we reconnect with persistent handles and also durable handles if you're limited to 2.1, but almost nobody is these days. Again, client A is accessing, and this could be accessing the same file too. I showed just the same share, but it could literally be reading and write. Well, they can be reading and writing the same file, but they'll lose releases if they both try to write the same file. But all the writes then have to go to finally be resolved on the server. And then if it basically loses its connection for some reason, with persistent handles, that connection is reestablished, and it comes into our software load balancer. It rehashes the TCP headers, and so it just picks a different front-end node. And that front-end node then establishes a new SMB session, and with persistent handles, part of the protocol is that the client just silently reconnects all those handles, so the application isn't even aware anything happened. There's a slight hiccup, maybe a second or so, for those reconnects to happen. But otherwise, it's seamless. It's called continuous availability, and it's seamless. In Windows, persistent handles are usually only used with SQL Server and other operations that are specific applications. In Azure Files, everything is persistent. Because again, we have so many of these disconnects when we're updating software on a node or just having flaky networks if you're going over the internet, that it was absolutely critical that we have this ability to seamlessly reconnect handles. Because otherwise, the value proposition of Azure Files is substantially degraded if you don't have this seamlessness about it. And so persistent handles was a really good fit for us because it really allowed us to implement this seamlessly.
Where do you persist?
In that back-end store, in this Azure table and blob store. And again, this is a durable store that is also used. There's also REST APIs to use those directly, blob and table. And they're replicated whenever you do a write. It's replicated 3 times in data center to start with, and they're potentially erasure coded at a later point. And so, for instance, when you open a file in Azure Files, there are several things that happen. You create a handle row. We increment open counts. And all of those have been replicated to 3 different physical clusters in the data center before we act that open. So in other words, before we send the response to the create SMB command, we have replicated all the state that we need to reopen that file in 3 different places in the data center. And it takes about 8 milliseconds or so. But that's like 2 or 3 orders of magnitude slower than your local file system if you're directly connected to like an NTFS local volume, which is why sometimes there are performance assumptions if they think it's going to behave the same as their local attached storage, which I have more details about that. These are some examples when I was talking about the state tiering, how we're able to go and conserve what we have to durably commit and what we don't. Again, things that can change and things that can't. Durable handle reconnect. I talked about this using that example when the arrows were moving. Durable v2 is actually where persistent handles come in, but it's very important for Azure Files in order to have a reasonable semantics and behavior that clients be able to reconnect their handles seamlessly, so that applications that are written especially legacy applications that you're not even recompiling, you're just running an existing application, it expects these operations to be reliable. Often they don't check return values of functions, so they just basically have to work. Persistent handles are the more functional form of durable handles that were added. You have to request them, and they were new in SMB3. That was one of the major milestones for us, is when we enabled SMB3, is persistent handles was a must-have part of that. SMB3 has basically 3 optional features, big ones. There's persistent handles, encryption, and direct releases. Encryption we needed to support connections from outside the data center. And then direct releases was the last one that we did, which helps. It's a performance thing, though it also potentially correctness, because by default, out of the box, Windows, the way it works around this, has a 10-second timeout on directory enumerations. But that's not correct, right? And when this was first introduced, I think maybe Windows 8, I was debugging problems where people were using multiple machines, would actually try to create almost semaphores using remote files, whether the file exists or not a remote share. And so you'd have these distributed systems that were depending on this behavior by doing durs to see when a file showed up. And that all broke. And so you had to kind of learn I've got to go change these settings to 0 in the registry. And that was, over the years, many people have learned that you have to go and turn off these timeouts. And with direct releases, you don't have to do that. But you get the benefit of not having to worry about, in the very remote case, something does change in the directory. You don't have to worry about continually going back to but yet you get the correct semantics. So it really is, direct releases are a good thing. This is going into from when we first put out Azure Files, and then looking at real customer feedback and some of the pain points customers have had, and how we've basically kind of addressed them and dealt with them going forward, and also how we've discovered certain problems in the Windows client, and also that have been now that can be ported to the Linux client as well, that are particular to our latency makeups, and how we basically our characteristics about that. Again, the most common one is people that hadn't even tried to run their application even against a local share on-prem. And then they're in for a big surprise when they try to open 1 million files that don't exist. And each one of those is a network round trip for us. Whereas in a Windows locally directed, if you have a directly connected NTFS volume, by the time you start doing enough opens, basically all the MFT records, all the index buffers for directories, they're all in memory. So at that point, it's just cycles. And that can be very fast. You're talking 10 microseconds, or if even that, to basically fail some of these opens. But of course, it takes us several milliseconds to find out that file doesn't exist. And so that's been kind of an education process with some applications where they can modify them. It's like you have to actually go and start looking at your application and how many superfluous opens it's doing. And things like open a file, write a byte, close a file, open the file again, write the next byte, close the file. Things like the behaviors like that. And so that, because one of the key value aspects was this, what we call lift and shift. So you can take an existing workload that was written for on-prem using simple Win32 APIs and run it against Azure Files. This is kind of a breakdown that we did. Actually, did this about a year ago. Just kind of curious, what are the requests that are coming in? And since this is averaged over an entire tenant, which is a whole bunch of lots and lots of accounts, it gives an idea of a statistically significant breakdown. And you can see here, reads, writes, closes, and open, close, read, write are the really big heavy hitters. And the reason there's two different scales here. One is measured as percent of total requests, and the other one is percent of total time in those requests, right? Because things that take a long time get more weighted in the right chart. And so that gives slightly different results. But still, the same thing is true, that it's basically open, close, read, write. So if you're looking at your application and what you can potentially that you can do less of if you don't really need to keep on opening and closing the handle, is to do that, to basically go and look at optimizing how long you keep handles open for. Though with handle leases, as long as you don't have multiple clients accessing the same file, handle leases should actually save you in that situation. And they generally do. But again, if you have situations where it's a distributed application, they need to be aware of how this impacts them.
What was this data set was observing something just random?
Yeah, it was just a period. I took, I think, over a month on one tenant about a year and a half ago, and just looked at all we collect some of these statistics and just, I haven't done over all of Azure yet. This was one data center, I think somewhere in US West. So yeah, it's not worldwide. Leaked handles have been a particular pain point because Windows has this semantics that when you call delete file API, it doesn't actually delete the file. What it does is it calls a set, yes?
It really surprises me that the amount of query info is so very, very small. Do you have any?
That's why I was asking that.
Yeah, well, Corey.
Sorry. I mean, that's why I asked the question.
Well, I mean, look at it's actually the 1, 2, 3. It's the fourth. So on the total number of requests, it's actually more than reads. So we get more query infos than reads, but they're really fast. Because if it's stuff that we like this, again, if it's this immutable state, we can cache it on the front end. We don't even have to go to the back end. And just in general, it's very fast if you're only querying some info. So that's why you can see the difference here between the size of this wedge here and the size of it here. So there's actually more query infos than reads, but they just take so much less time because they're very fast. So in a way, the answer to your question is there actually are a lot of query infos. They just don't add up to much.
So it turns out it's what's being queried is, I would have expected the opposite, it would be bigger. But the queries tend to be for this more immutable state.
Yeah, and it's returning a small amount of information. At some point when you're reading, what starts predominating is just the time to transfer the bytes, right? If someone is reading, hundreds of megabytes, that all adds up into the chart on the right. Whereas we never return query info always returns a handful of bytes, right? Never very many. So there's never, in other words, what's built into the read and write ones on the right side are the transmission times, sending the actual data, whereas there's no such cost for query info. Does that make sense? Yes?
This looks like a write-dominated workload.
And this is because at this point in the life cycle of Azure Files, there's probably a lot more data coming in than going out. So that was kind of interesting as well. We kind of thought that, well, it's interesting. They're writing a lot, but not reading as much. And about a year and a half ago, that makes sense because a lot of people were copying data into Azure Files and not necessarily copying it out. And also, we don't charge for ingress, but we do charge for egress. So it's free to copy data in, and then, of course, we charge once it's there. Once you get, so yeah, bring it in, and then we'll charge for it. And then if you copy it out, we charge for that. But that might also have something to do with this.
Can I delete for free?
What is that?
Can I delete for free?
Yeah, you can. Well, no, actually, then there's transaction costs too. There's a per transaction cost, which is very small. It's a tiny fraction of a penny, but they can add up. So you want to be careful of these transaction costs. But yeah, generally, it's a very small cost to delete data. Leaked handles, as I was going into the delete file API in Windows, it doesn't delete a file. What it does, it sends a set disposition call, which marks file for delete. And then the file itself doesn't get actually deleted until the last handle is closed. And this is very different than the Linux unlinked semantics where the file goes away right away. So you have people that are running Linux applications targeting an Azure Files and then also have all these problems because the files don't go away. And in most cases, it's been because they're leaking handles because it doesn't matter to them, right? They're not being strict about closing handles. But this still causes customer pain, and we spent lots and lots of time with customers walking them through what happened to their handles. And we tell them, well, you opened it from this IP address at this time, and then they can go through their logs, and usually we never hear from them again because with that information, they're able to go through their internal logs and figure out who's leaked the handle and fix it. Occasionally, there were actually 2 bugs in both the Linux client and the Windows client. And interestingly, they were actually very, very similar situations dealing with failed opens. anyway, we fixed both of those. And that was a case where it wasn't the client's fault. It was simply a bug when I say client, it wasn't the customer's fault. It was a bug in the actual redirector. And that was an interesting case. But in both of these, to handle it, we've added a new REST capability to force closed handles. This is similar to on a Windows server. You can do net files ID/close, and that force closes a handle on the server. We didn't used to have a way to do that. And so when that happened, we would have customers call us, and then I would literally have to go and hand edit tables to force close their handles. And that doesn't scale. And so we now have this REST API that we've introduced, which allows customers to close their own handles, and they can query their own handles. Yes?
All the handles are supposed to be closed when the session goes away.
It depends. Yes, it's persistent handles. We give them two minutes to reconnect, and then otherwise, yes, we'll go and scavenge them. But this is a case where the session's not going away, right? So say an app that has a bug that leaks an open handle. They haven't closed their session. They just leaked an open handle. And they've got a process running with this handle, and then the file's not going away, and so they call us and say, why isn't my delete working? Or my unlink in this case. Because they thought it should have, because they called our set disposition information, but until the handle count goes to 0, we don't actually delete it. This is also a problem with directory rename, because in Windows, you can't rename a directory if any of the children beneath it have open handles. And that's another case where we have to try and figure out what are open the handles, and I give them lists of like, okay, you opened it, these handles at this time, and then they can hopefully find where the problem was. And so having that server management that people are used to on-prem by having the ability to force close handles is very valuable. And I only have a couple minutes left, so I'm going to go into this one is evil, fopen foo a for append mode, because it opens it for write-only access. And it has to do with how Windows caching works. But if you don't open a file for read caching, then I can't cache it locally because I can't fault that data in because I don't have the rights to read it. And so what that means is every write, even if you have an exclusive lease, has to go over the wire. And for people that do a fopen and then write 1 byte, write 1 byte, write 1 byte, that's really, really bad because it's 1 byte writes every single request. And if they just added read access to that, so read-write access, the problem goes away. But then we have people tell us that they're philosophically opposed to it because they don't intend to read with the handle, so they don't want to specify read access. And this is just kind of there's potential fixes within the Windows client to get this to special case this one of people appending a file, because that's when this happens most that I've seen it is people appending files, and we could potentially special case that one. Variability in performance, people talking to a local disk, you pretty much get, depending on outer ring versus inner ring, but I mean they're pretty much very similar performance. You get wildly different performance on the public cloud because of noisy neighbor effects and just various things. Hardware going bad and having to fault over different partitions. You can get these hiccups that can last sometimes several seconds. Shared namespace with REST. REST goes over HTTP, and as such, it has certain character set restrictions that we don't have over SMB, because over SMB, it actually uses UCS2, which means it's literally just a bunch of U-shorts, right? There's really no attempt to find invalid surrogate pairs or anything like that. Whereas REST has some much more specific limitations on what characters can be sent. Even if you escape them out, there are still more limitations. And so that potentially causes a problem. And then in general, just poorly written apps. I mean, people that were able to get away with things on a locally connected storage because local file systems are really, really fast. Everything eventually gets into memory, and so you're not doing any disk I/O at all, and so you can get kind of complacent. But when you're doing operations that have to especially go over the internet, and then everything's being triple replicated every open you do, it's important to make sure that you're doing those conservatively. These are some resources about Azure Files in general, some of the naming restrictions I was just talking about. We don't currently support all NTFS features, like name streams, for instance. Hard links, and those are listed in that page there. And just there's a blog that has some useful links. And so that's it. And out of time.